see if, yeah, it works. Yeah.
Yep. Okay, thank you all for joining the Matrix AI seminar series. As a reminder for students who are in the research seminar, the master's and PhD seminar, please make sure you're compiling all your summaries and submitting them within the next week or so. And today we have a very distinguished speaker joining us to share some of his research in massivizing computer systems. We have Dr. Alexandru Iosup, who is a full professor at VU in Amsterdam, which is a very top-notch research university in the Netherlands. He's a tenured chair of the Massivizing Computer Systems Research Group at VU, and he's also a visiting researcher at TU Delft. He's an elected chair of the SPEC-RG Cloud Group, and he has published extensively in distributed systems and ecosystems with high scientific impact, and has applications in cloud computing, big data, scientific and business critical computing, and also online gaming. And he has received several awards for his work, including membership in the Royal Academy of Arts and Sciences of the Netherlands, the Netherlands ICT Researcher of the Year Award, and several others. And he's also received the Netherlands Higher Education Teacher of the Year Award for his educational efforts, and a knighthood for cultural and scientific merits, and the list goes on. We are indeed honored to have Alexandru join us today to share some of his research in computing systems. The floor is yours, Alexandru.
Thank you very much, Dirisha. Thanks for the kind introduction. It's much longer than what a Dutch introduction would say, which would be more like, "Hi, this is Alexandru. Go on." So thanks for this. Thanks also to Gabriela for inviting me here today. What I'd like to talk about is a small part of what I try to do. I'm going to talk about massivizing graph processing. But in general, if there's one thing, okay, let me try to see if my clicking actually works. If there's one thing that I'd like you to remember at the end of this talk, is this notion of massivizing. And it's a rich challenge of computer science with high societal impact, which simply says that when you actually have computer systems and you put many of them together, you get to do very interesting things, very useful for the society, in this case, graph processing at scale. But it turns out that putting these computer systems together is particularly challenging. It raises all sorts of issues of performance, availability, energy efficiency, you name it. So it's particularly difficult. So one thing to remember today, massivizing computer systems, it's a term, it exists, it means something. Okay, so I'll try to convince you that even if you shrink down the whole problem of massivizing computer systems to graph processing, there is a science of this, there is a good field of design in this space, and there's a lot of engineering, and the outcome is always a complex ecosystem. I'll explain all these terms, don't worry. If everything goes down the drain, somehow my internet connection fails, whatever, just go to this bit.ly short URL, and perhaps Gabriela can post it in the chat. I've sent it to her over email, so maybe you, Gabriela, can post it in the chat while I speak. All right. Then about us, well, it was a very nice introduction, so I'm not going to say much more. Good university focused on research. It's very close to Schiphol, so you can just fly in without trouble. Then my team itself, so we're actually quite many, because computer systems is the kind of science that actually works as a big science, works as a science in which you need to have connections with all sorts of scientists and engineers and designers in all sorts of areas, and then you put everything together and you make it run. Perhaps interesting is that we are hiring. So if you're interested in the topic, just let me know. We're a nice team, we're quite diverse, and we welcome everyone, who knows how to do their job. About myself, I think enough has been said. I have also the unique advantage of having a name that is very easy to search. If you Google, I'm either the first or the second reference. The competitors are the International Organization for Stand-Up Paddling. So it's either them or me who, in this competition will get somewhere. All right, enough about this. Perhaps more interestingly, I co-lead the current manifesto on computer systems and networking research in the Netherlands. Here is where we say what we would like to do in this field in the Netherlands for the next 15 years. This is what we hope the government will be funding during this period. So if you're interested, just have a look. You can get all these links from the slides. Again, they are online. And a project that is upcoming in January 2023, we really want to massivize graph processing. So the topic for today aligns nicely with this starting project. If you're interested, I can say a lot more about it today. I'll use, I think, a couple of minutes only for this. So the first point I want to get is something that should not be contentious. And I think it would be something that we should be able to agree on. I think this is the golden age of computer ecosystems. Here is what I mean by it. Well, if you look around you, then a lot of our lives have moved digitally. What we're doing now is education online for everyone, but also big science. So just science that approaches the big problems of the society, all sorts of business services, including online shopping, definitely online gaming, your daily lives, maybe online banking rings a bell. All of these are basically applications of massive computer ecosystems. What do these massive computer ecosystems, what are they comprised of? Well, definitely some form of connectivity, and you all know about the internet. You might also be currently users of 4G or 5G in terms of wireless connectivity, but there's a lot coming up that we are involved in, 6G technologies, terahertz, VLC, etc. for connectivity. And all this connectivity brings data from these applications towards massive IT infrastructure. So you may have heard terms such as, I don't know, from grid and HPC computing to cloud computing, the current darling of the industry, big data processing, maybe even beyond the computing continuum can include the edge, IoT, all sorts of other terms, fog, etc. All of these simply capture different parts of the IT infrastructure, different kinds of computer systems, which put together form massive computer ecosystems. They take the data from these applications, they process it in various ways, and they return meaningful answers. So that's the space in which I'm operating. I find it fascinating, but also you could recognize that a big change in the last, I would say, 5 to 10 years is that AI is very broad, but especially machine learning is starting to catch up and be included in all sorts of these applications. This is something that you know about. But if you are also interested in IT, you might actually notice that AI and also especially ML get embedded in all sorts of these infrastructures, IT infrastructures. Now, the talk for today is about graph processing, so I can make a similar line of reasoning. I'll talk a bit more about graphs, of course, in the remainder of this talk. But for now, let's just agree that data represented as some form of entities or nodes and relationships between these entities or edges form the rather abstract representation of the natural world in the form of graphs. And these graphs are starting to be used everywhere. I'll give you a couple of examples in this talk. At this scale, it turns out that the IT infrastructure, these massive computer systems, are very lucrative. So every euro invested in Europe and in the US generates at least 15 other euros of added value. If you want, you can convert this into dollars. The ratio is the same. In the Netherlands, in particular, the economy has about 2/3 of it actually traversing these data centers. If even for 1 second they go down, there are millions of penalties in damage. If the whole infrastructure goes down for, let's say, a month, then 2/3 of the Dutch economy goes down. So the notion of golden age is pretty simple. Not only almost everything we do is actually using these massive computer ecosystems, that's the nice benefit, but also we have a responsibility to actually get these systems to actually run for everyone and be online and responsive and active and high performance at all times. Otherwise, the economy really suffers and the society really suffers. So here comes the but. Unfortunately, this technology, it's all around us. We all use it, whether we know or not. Unfortunately, we can't really take this technology for granted. So if you think about graphs, they are everywhere. So I could argue that there are lots of useful applications. Here you see three of the larger graphs that I can imagine, including the graphs for LinkedIn, which are really essential for you getting the job, me maintaining my job or something. But also social and gaming networks, also attempts to understand simply the brain network that humans possess, and with this do all sorts of either reasoning automatically or repairing the brains of people who actually might have suffered some damage. All of these are really examples of massive graphs. And what's the challenge? Apparently we have the graphs, we have applications for them. What's the challenge? Well, if you want to actually mine even a relatively good size, but still not the largest, a relatively normal professional network. And here is one of my dear collaborators, Anna Lucia. She will appear a bit later. She will tell you something about graph performance. She was the first in the world to formulate this. But if at some point you wanted to mine your professional network to understand a bit how it's structured and what kind of properties it has, well, unfortunately, LinkedIn would return such a message, which is an error message stating that simply LinkedIn at that time did not have enough performance to compute on these kinds of graphs. Again, not the largest possible, to compute the various statistics that would be interesting. In fact, the situation was so bad that LinkedIn even stopped the service altogether. So they couldn't get it right. Performance is not the only issue. Failures also occur quite frequently. Whenever I talk about failures, I like to give examples from online gaming, then everyone feels safe. Because when I talk to, I don't know, let's say bank C-level officers, they don't want to hear that the banking system has exactly the same properties, but it does. So also the banking system has high unavailability and failure issues. There is also the not small issue of climate impact. So when these IT infrastructures were small and, each of us had just a few computers and we were playing with them, it wasn't a big deal. But now when the entire society is using them, the Jevons paradox indicates that, the better we get at making this infrastructure, the more use it will get and the larger and more scaled the demand will be. Which means that even currently, IT sustainability, just that we are not impacting the climate too much and we know what we're doing, this becomes a major problem. So electricity is a big issue. IT infrastructure consumes lots of it. Much of it gets produced in, not very sustainable ways. But there are also many other impacts in terms of climate that we still don't know that much about. And the last issue that we can observe is that actually few can operate these kinds of complex IT ecosystems. So I've mentioned LinkedIn. They are actually one of the companies that can do graph processing because they could find enough hires, enough people. But in fact, the situation in Europe, in the US and in other places in the world, but in particular in these two vast geopolitical areas, is quite dire. There are hundreds of thousands of experts that are needed. And even if all universities would just function full tilt, it would take 20 years to cover the current gap. So we'll see what happens there. But I will get back in my talk to this notion of, okay, if people cannot solve certain issues we have, maybe we can automate them. So I just want to say that at this point, we know that there are these massive IT ecosystems. They do, among other things, graph processing, also AI and machine learning in particular. But we need to do something about them because they raise many challenges that right now seem, some of them, even insurmountable. So what my team has been doing for the past, I would say about 10 years, I've been in the business for about 15. is pretty simple to, or pretty easy to summarize as we want to understand why does this, why does each challenge happen, and second, what we can do about that challenge. Point A is a typical scientific point. Point B is typically addressed with design and engineering. I'll get back to these notions. So also, if you have any question, just don't hesitate to state it. I don't know how to enable that you can say things, but I think Stacy will do it. So thanks, Stacy. Then the first comment on how to approach challenges or problems in this field is that we need to learn how to combine science, design, and engineering. And I'll take a step back and I'll say that one of the most famous persons combining science, design, and engineering, and also art, but that's something that I cannot teach, was Leonardo da Vinci. And if you look at the drawing on the right, then you see a very nicely formed Mona Lisa. It took him almost his entire life to get to paint it, and he tried over and over and over again. The reason for this, or one of the reasons, is that simply he wanted to understand everything related to the process. For instance, he wanted to understand how people would perceive the drawing, which, as you may notice, is drawn in an unusual way. There are no contours, there's fumato, etc. So he actually did a good analysis of understanding how humans would see things. That's the drawing here on the left. So he was one of the first theoreticians of how the brain actually interprets images. Now, not every painter needs to know how the brain functions, but Leonardo was one of those people. The drawing includes also water. So Leonardo, of course, did empirical studies of how swirls in water actually work. He's still cited even today. So science has not evolved that much that his intuitions or first discoveries are unknown. I can go on and on, but the point is that he really combined these different things. So let me explain, of course, we're not Leonardo, but let me explain how science, design, and engineering could work in this field. Let's assume we have a particular task. So at the beginning of the COVID-19 pandemic, we really wanted to know how to process various information related to the disease, both social networks, so understanding how people react to this and who are super spreaders, etc., and also biological networks to try to understand whether we could synthesize, I don't know, drugs or vaccines that could help with this. Turns out to do this, we would need to build a complex workflow. Workflows are simply collections of tasks, of things that need to be done with interdependencies. A particular task will not be starting until its predecessor has either completed or produced at least something that the follower can actually use. So it turns out that we can model the entire graph processing workflow, includes many different things, data management, graph extraction, all sorts of post-processing and even data warehousing, also some more, let's say, deeper analysis, things like machine learning, scientific computing, the rest. All this stuff needs to exist, be engineered, and actually run. And it needs to run at the proper speed, so with the right performance. Otherwise, nobody can use it, at least not for something as important as finding answers in the COVID-19 pandemic. So this raises as a question how to actually build the graph processing part of these workflows. Well, you could write your algorithms for graph processing, but some platform needs to run them. And it turns out there are literally tens of specialized platforms, each of them claiming to do any kind of even general graph processing. But in fact, the reality is quite different. So if you want to know which of the tens of specialized platforms you could use for your own, I don't know, COVID-19 workflow or something similar, then you need to answer the question of how well the graph processing platforms perform. And on the basis of this, maybe be able to select the best one for your particular case. You could try to do this with theory, so with science. The only problem is science at this moment does not have the right models, cannot explain what happens when multiple computer systems get put together. And these platforms are always combinations of tens to hundreds of computer systems put together. So there's no science that can tell us how these things run until we actually run them. Okay. So there's a lot of there are lots of experimental methods of discovery, trying in practice these platforms and seeing how they run. This is what we do either on our large experimental research infrastructure that does, I don't know, 4 or 5. Right now we're at the 6th generation and we're acquiring funds for the 7th, or by going to Amazon, that's also fine. So going to a cloud, or by simulating various situations, but simulations are based on models. So those models can only be derived, lacking the proper theory, can only be derived or inferred from real world experiments. So that's what we set to do. We looked at these many different platforms and we thought, well, how can we actually understand their performance? Can we compare them? So we started to actually think, well, all of these platforms can run all kinds of graph processing. Can we at least, you know, using some taxonomical style of thinking, can connected to the network? Can somebody say yes or something to see that I can be heard? Yes, perfect. Okay, super. So workload is a term in computer systems indicating what systems need to do. There's a specification for this, and there are also some software packages that get moved left and right, and then the computer systems run this software and execute the workload or complete the workload. Turns out in graph processing, there are many kinds of workloads, but if we think about the level of detail, that's the axis or the taxonomical axis that is horizontal, we can look at whether the analysis that the graph processing is doing is based on structure, or structure with some sort of numerical weights added on the edges, or possibly also to nodes, or the highest level of detail, there are actually properties, and properties can be numeric or textual, doesn't matter. On the vertical axis, we can see roughly what kind of temporal expectation we have to this analysis. Should it complete quickly? Is it okay if it runs for much longer? Well, if we put many of the graph algorithms, so BFS, PageRank, they're classic graph algorithms. You learn them typically in the bachelor's first year graph network analysis. Dijkstra, Floyd, there are names of big names in computer science. Dijkstra won a Turing Award. And the right-hand elements are bigger kinds of analysis. If we try to taxonomize these, then we know already that we could have business intelligence with the highest level of detail, but we could also have simply graph analytics. And graph analytics typically precedes any kind of other analysis, any kind of business intelligence, and it's the first step that you take in a field once you move it not to digital data, not to binary data, for example, but you move it to graph data. So this is a space in which we work with something we call graphalytics. We are the creators of this, but by now it's much larger. So there are many groups in the world that work within this space. So simply this part of graph processing techniques. Now, with graphalytics, we want to understand the performance of graph processing platforms, as I mentioned. And also here we can taxonomize the kind of understanding by the breadth of understanding. So should we run as the workload a single job and report for it a single metric? Let's run one of the algorithms and report, let's say, the number of traversed edges per second. By the way, this is the approach of Graph 500, which is one of the largest or most used benchmarks in the high performance computing world. Or should we be deeper, so use many more metrics? Or in the breadth dimension, should we try more diverse algorithms, more jobs, more data sets, etc.? Well, with the graphalytics ecosystem, we're actually covering the entire spectrum. So LDBC graphalytics is a collection of algorithms. I'll return to this. So more algorithms, more metrics. Grade 10 is a very deep analytical tool for the performance of graph processing systems, but it reports metrics, for example, or can use per particular elements that are not available for every graph processing platform. So in that sense, it's more of a specialist tool and works only for some platforms. And we also run a global competition where we use a single value of merit. So the depth is very low. but we use many different applications, and because of this, the breadth of the competition is quite wide. It's quite a good competition. So what is this graphalytics? Well, it's actually an engineered benchmark. So it took us about 7 years to get to the current level. We engineered it for 2 or 3 years until we released it. It takes a long time until a bit of software is well engineered enough that it can be used in production. It is currently the graph analytics benchmark of the Linked Data Benchmark Council. This is a global organization that runs benchmarks for graph processing. So Graphalytics uses many classes of algorithms used in practice. It can generate data sets at any scale. It also provides real data sets for what we call right now medium-sized scales. It proposes different kinds of experiments for which it reports certain kinds of metrics. It has a renewal process. So, in time, whatever definition of a benchmark you have, it should be subjected to further scrutiny. So there's a renewal process for Graphalytics that allows this. It automates the comparison of the performance of really many platforms. Some are industrial, so they're really making money for different companies. Some are community driven, so especially academia driven. And because of this, they might not care about money. They might optimize only for some things, etc. And also this Graphalytics is the core of a global competition. So any graph processing system can be benchmarked with. Any graph processing system that runs graph analytics as the workload can be benchmarked with this. And it enables manual auditing. So what did we do with this? Well, first, we got a benchmark that is really community endorsed. So right now, Graphalytics is the de facto standard in the industry. And that is the consequence of good engineering. So you really need a benchmark that is well engineered. Otherwise, people cannot use it easily, and they don't. But it also generated science. So by running experiments with Graphalytics, we started to actually find interesting things. I'll explain this finding, but for now, let me just state it. We found that the performance of graph processing platforms really varies by even orders of magnitude due to the platform one selects, the algorithm, the data set, and even the platform can include both software and hardware. So both have strong contributions to performance. In other words, when you try to understand the performance of any graph processing system, you cannot ignore any of these main components. Otherwise, your performance analysis is not good enough. This is, by the way, pretty bad news for the community because it means we can hardly fully optimize these platforms. There are simply too many dimensions and nobody has done it across all of them. All right, so how did we find these kinds of things? Well, we ran experimentally using Graphalytics as the benchmark. So we run the workloads defined by Graphalytics in an environment that is the same for all the platforms that we deploy. And then we measure different kinds of metrics, including the runtime. And here you see examples. So a plot depicting three subplots. The results we got for 4 of the graph processing systems, Giraffe, GraphX, MapReduce, and Neo4j. But we tested more than 10 such systems. So for simplicity, I'm just depicting these. The vertical axis is the runtime. Lower is better. Note the logarithmic scale. And then the finding is that there are orders of magnitude difference due to the platform. So if you select the right platform, apparently you're good. But the different subplots also represent results for different data sets for the same algorithm. So in this other plot, we're trying to really emphasize the impact of the data set. And here you can see that for one algorithm, the same algorithm, for one data set, this Graph 500 size 23, which is a medium scale size, a particular platform, Neo4j, performs much better than another, MapReduce, by a factor of 2 to 1. Then for another data set, it's the opposite. And for yet another, it just happens that one of the platforms is even unable to complete the job. It simply crashes. So the data set also has a very large impact. I won't go through all the results we've gotten. We've done close to 10 years of measurement. The observation which Ana Lucia Verbenescu introduced in the community is simply that the pad triangle is a function that needs to be explored and understood, the function of platform, algorithm, and dataset impact on performance. And you can't typically get away with any two or any single element that you take here. You can't predict performance by just measuring, for instance, performance for different algorithms. Okay, turns out in the community, the link between algorithm and platform is overstudied. Everyone looked at this. Unfortunately, you also need to look at data sets. And you really also need to look at the impact between, or the interplay between data sets and platforms. And this can also indicate where the research will probably go in the next 5 to 10 years. So once we found that there is this situation, we started to ask, okay, but why? So we triggered new science and we realized that we actually don't have the right instruments to understand why. So a benchmark you can, construct it with reasonably little design and a lot of engineering, but to actually do performance analysis, you need to do things that are much deeper. So here is our grade 10. It's part of the Graphalytics ecosystem. What it does is it automates bottleneck detection. It goes in a lot of depth in performance analysis, and with measurements, modeling, and automated analysis, it identifies or spots particular points of trouble, and also identifies what's the impact of those points of trouble on the overall performance, and therefore allows you to focus on the most interesting bottleneck. So without this, by measuring different things, by benchmarking, for instance, we cannot tell if there's a particular bottleneck in any particular platform. In this example, Apache Giraffe, an open source platform that everyone can check, has been engineered for many years, so we were not expecting to find many bottlenecks in it. But with grade 10, we actually found that almost all the time, grade 10 suffers from big bottleneck issues. So here is how an analysis would look like. In this plot, horizontal axis is time, vertical axis is the use of the key resources. In this case, it's a compute-intensive workload, so we expect the use of CPU cores to be high. And what happens in each iteration is a plot like this describes how does the graph processing system, in this case, this giraffe, is actually running one iteration of a graph processing algorithm. Under ideal circumstances, the CPU usage will be below the total presence of CPUs in the system, so it will be below the number 32. So if I'm looking at this plot, there should be no bottleneck. The system simply has enough CPUs at the disposal of the graph processing system. It should not be a bottleneck. Turns out that if you actually analyze this, and again, all this analysis is automated, then first we could look at what the compute threads are using out of this giraffe application. And we could argue that, these horizontal axis is still time aligned with the plot. Vertical axis is whether during a particular period, the bottleneck of these different kinds of resources actually manifests. And here you see that there are some small bottlenecks, but not big enough that they would be a threat. The time is on the horizontal axis in milliseconds. So what you see here as the black bars are just a few milliseconds, and therefore they elude or escape most traditional tools for analysis. But even these are not the really important bottlenecks. Turns out that other components of the system are and really limit its performance. So my conclusion is that by using the right tools, the right instruments, which still need to be developed, you can actually find, the right places where you have bottlenecks in computer systems. Giraffe is a computer ecosystem, combines multiple systems in one just to run. Great. So let's assume we can do this. Then the remarkable finding out of the Graphalytics ecosystem is simply that performance is not as easy to predict or understand as just much of the previous work was doing, but also some bad news. If we want to improve our systems, turns out that there are a lot of bottlenecks that were not identified before, and there must be a way to improve them more systematically rather than bottleneck by bottleneck. Fixing one bottleneck may actually make things worse for other bottlenecks, so that it's not a good approach unless there are just a few of them. And we just showed that there are actually way more than we thought. All right, So what can we do about it? At this point, I'm going to try to rush. And Gabriela, please cut me off at any time you see fit. So what we can do about this is what I call a new science. It's a science in which we want to work with ecosystems or concepts around ecosystems or computer ecosystems to try to solve the problems that we actually observe in real world IT infrastructure as opposed to, modeled, highly synthetic IT infrastructure that appears in the current science. The intuition, I think, is reasonably simple. In climate science, many of the issues are actually linked. Here you see from Bjorn Stevens' talk at Supercomputing a couple of years back that understanding in climatology what will happen, for instance, in weather involves understanding first or identifying what are the weather systems and then predicting their dynamics, not independently as was done maybe 100 years back, but actually, when these different systems get coupled, it's one thing for these two weather systems to collide and form a super storm, a Cat 5 storm that is really damaging, can actually end lives, and you need to move people from its path. Or the same weather systems can collide and fizzle out, and then you get, a reasonably pleasant bit of wind and a bit of rain, but not much more. And then you don't need to move people around, and people will not die. So without actually having the models and the computation that allows to couple and combine different systems into the same analysis, you're not doing much in climate science anymore. And the same happens in computing. What are these ecosystems? Well, we think that they are simply combinations of these systems. They're typically heterogeneous, so they do different things and they work together. For giraffe, there's a part that processes and a part that stores things and a bunch of other parts, each doing its own stuff. Each constituent is a system, so a computer system or even something larger. For giraffe, many of the resources could have come from the Amazon ecosystem. The constituents are autonomous, so that deployment of giraffe can be taken out without Amazon having anything to say about it. And ecosystems use their structure and organization to, ensure certain responsibilities, such as completing particular functions, so running, for instance, a graph processing workload, providing desirable non-functional properties, for example, good performance, and doing this under certain service level agreements that are predefined. If the system cannot meet these, there's a penalty, etc. And now the part that has been ignored by the current science is that there are actually long and short-term dynamics, and these need to be accounted for and actually dealt with. Otherwise, the systems misperform or do things that are completely different from what the science predicts. How does an ecosystem really look like? Well, I've mentioned that there are these digital services that basically build a graph processing workflow or something similar. They need to run on computers. On the horizontal axis, you see time. On the vertical axis is the intensity of the workload. There are peaks, there are valleys. Each of the executions actually needs to be coordinated with hundreds of other systems, forming an ecosystem. Where do these things run? Well, in rather large IT infrastructure. So typically data centers of any size. That's why it's a computing continuum from the smallest, just a few kilowatts, to the largest hyperscalers. They are in the order of gigawatts. And if everything goes right and the resource management and scheduling system powering this computing continuum works well, then we get automation, performance, dependability, sustainability, all the right properties. So what can we really do? Well, with high-level approaches, we can actually guide what we're studying. So one is to understand that the entire ecosystem that I've mentioned hundreds of different pieces of software and hardware that need to be coordinated or orchestrated. We actually have good reference architectures that indicate how these different particles combine and which roles do they play. So consider this a bit the DNA of the data center. For graph processing, it looks like this. For AI and ML, it looks very similarly, except that the parts that need to be coordinated, these blue boxes, are many more. And the observation, both for AI and for graph processing, is that actually the applications actually are very small particles. Everything else around them gets automated and coordinated without the developer of the application knowing. This is what we call the modern world of either cloud computing or, if certain properties are met, serverless computing. Okay, Then I've mentioned that we need to do smart resource management and scheduling. Well, what does resource management and scheduling mean? It means a combination, the right combination with the right configuration for the problem at hand of any number of operational techniques. And here I have 10 that are actually combined one with the other. At least there's a visual explanation, a taxonomical based explanation based on a Venn diagram. What's the relationship between these different resource management and scheduling techniques? We are the first to propose a synthesis of the entire field across all these different operational techniques. So the community should, we think, really explore systematically all these different techniques, knowing that in a system you typically have all of them active. Yeah, but of course with different configurations and different ways of thinking about it. Okay, I've spent about 15 years in trying to do anything having to do with allocation and provisioning, and I've barely scratched the surface. This is really big. And the last point is that we should very systematically define also how our workloads get actually run, and that they should be reproducible. So once you run some AI job, it should actually be reproducible. If you run a graph processing job, you should actually know that if someone else reruns it, maybe 10 years down the line, or even 100 years down the line, they should get the same results. And how to do this? Well, we hope with a community-driven common workflow language. So you see our publication in Communications of the ACM, the nature of computer science. Okay, more practical approaches, and in 5 minutes at most, I will end. Well, the practical approaches are really very detailed. So I don't have the time to go through all of them, but I will emphasize 3 firsts in the world that we did in my team. So the first, distributed heterogeneous system for graph analytics, we did this. And the idea was that until we stepped in, there were many distributed systems for graph analytics based only on CPUs, so they could only run on central processing units. And there were a few that were GPU enabled, so could actually run workload on GPUs. But they could not exploit both of these resources simultaneously. So what we did is we explored systematically every design or architectural combination we could imagine, in particular 3 in this work, but every possible combination, architectural combination that allows a graph processing system to use both CPUs and GPUs, and in that sense to become heterogeneous, where the CPUs and GPUs are not only in a single machine, but also distributed across many different machines. Turns out, so these are the visual summaries of the architectures. Turns out that especially for much larger data sets, it's convenient to actually do this. First, you get good performance. And second, you're able to run with this architecture, distributed and heterogeneous processing, you're able to run much larger jobs, so much larger workloads, either for larger data sets or for more computation that others cannot. Turns out that this was a good idea. So many modern systems now, like 6-7 years after we started, are really following this hybrid approach. What else can you do? Well, you can make your systems elastic. So elasticity is a property of a system to adapt to workload. If there's more of it, then the system increases the number of resources allocated to that particular job, and then that workload gets satisfied. If there's less of the workload at a particular time, then those resources get freed and used for something else. It's a very efficient way of scaling. And auto-scaling is currently used by all cloud operators, so it's a way to do this automatically for the user. Turns out you can do elastic graph processing, in particular elastic graph analytics. We were the first in the world to do it. And what you get, I'll just summarize the results. So these are results for 6 different classes of applications on a single data set, but we tried other data sets as well. And our observation is that elastic graph processing can actually perform on par in terms of performance with other JVM-based platforms. That's how we implemented our system, but it's much more efficient. So you actually use way less resources, and it turns out that modern systems are increasingly doing this. And as a last example, we built the first serverless graph analytics system. in the world. So serverless computing is about extreme automation. Your workload gets fully automated. And then there's a lot of fine-grained reporting, and only the part that your system is using gets charged by the system operator. So that's convenient. So what's serverless? Well, if you take an application at this point, the developer of the application still needs to think which part should go to which part of the cloud, which service or which machine or which service. But you could actually split this into business logic and operational logic. The business logic is what the application should do, and the developer knows a lot about it. The operational logic, well, that's the part that I just mentioned, the developer not wanting to do, thinking exactly which part of the cloud to use, etc. So why not give the cloud users, the developers, the task only of the operational logic and leave the operations to the experts, so the cloud providers. Turns out that if you take a typical graph analytics job, then the part that is the business logic is simply to run graph analysis. That's what the application should do. So with serverless approaches, instead of doing all these other steps that you see on the left-hand side, you let the serverless system actually do it, and hopefully it's efficient enough, because that's the promise of serverless. It will be efficient enough, and it will operate fine-grained and only charge for what is being used. Turns out we tried many different architectures. This is the best result we've gotten so far. Turns out you can actually run graph processing in a serverless mode. The performance penalty actually exists, but we think we know why it's there. It's this blue part of each bar that is way too large relatively to what is happening inside the computation, the other parts. So that's the part that we should improve. Now, we don't know if this will gain traction in general, but we think that modern systems will actually follow this hybrid approach. Okay, then I've given you high-level and low-level techniques. There are many different approaches. What we're trying to do now with this Graph Massivizer project is to put together all the things we know with all our partners. We have 10 partners in Europe. And what we want to do is to really make graph processing serverless, so really remove the difficulty from the users of and developers of graph analytics workflows. To do this is a quite complicated structure. Also, at the scales at which we envision this will be used, energy really matters. So we want to actually focus on energy optimization and provide also information to our users as to how much this is done, so that we're not just saying we've saved huge amounts of electricity. No, say exactly how much, and you know, cut the adjectives from the discussion, because we're scientists and engineers and not poets. One of the applications, and with this I will end, one of the applications that we envision is simply to take, one of our partners is running one of the top 5 supercomputers in the world by both scale and capability, Cineca in Italy. And what we want to do is to help them actually improve their operations so that their next supercomputers, which is about to arrive, will actually be very efficient. And also, efficiency is not enough. It's also a matter of when you use electricity and how. So we want to improve all these elements. The processes to improve this are data-driven, and the data will be graph-based. So that's our approach. It seems to be a natural mapping of the problem. Data centers are basically nodes, which are the computers with edges. These are the networks. And then there are other networks beneath, for instance, the networks that cool down the equipment once it's been used. And we want to combine these networks and analyze things over long periods of time to actually understand where are the places that we could actually improve or even optimize. Okay, so the take-home message. Well, I hope that you still remember that massivizing was the one and only message that that perhaps was to remember. It's a notion of computer ecosystems that offer interesting functional and non-functional properties for a lot of different applications useful for the society. Massivizing computer systems is about getting their components and putting them together so that they do offer these properties. Graph processing is definitely based on ecosystems. You may have remembered from the reference architecture how many different particles needed to be combined. The count is in the hundreds for even one algorithm that gets run well. And I told you already that there are high-level and detailed approaches to try to work with this graph processing ecosystem. We can study all our lives unless we're very systematic about it and still not find an answer. So I still hope that we can be more systematic about it. There are many open challenges. So if you're interested in this, let me know. And know that there is this Graph Massivizer project where we're also hiring with which we're trying to make serverless graph processing the reality. So thank you very much. You've been very gentle to wait for so long. Sorry for going so much over time. Questions are more than welcome.
Thank you. Thank you so much, Alex. Yeah, let's see if we have questions. You can just ask the question directly.
Okay, hi. Thanks for the talk. Okay, you mentioned several problems like reliability and complexity of these systems and performance and energy consumption. And you mentioned like LinkedIn analytics as an example. And yeah, I don't even want to know what LinkedIn piled on top of other stuff just to do their analytics platform. Like computers are insanely fast, and it's mind-boggling that they weren't able to provide an analytics solution for a few million users or whatever. So isn't one clear approach to solving this problem reducing these layers of abstraction we tend to pile on top of our analytics platforms? So trying to like find a better mapping between what problem we're trying to solve and the actual computer hardware that we're trying to solve it with. And I think projects like RENA and like looking at every layer of that system from the bottom up, that could be one approach. And I also like what you said about serverless. Like I think automation and providing a nice interface is important too.
So thanks, Alec. Thanks for the comments and the question. First, for some of the comments, computers have definitely increased in speed. In fact, they're the fastest improving technology that the humankind has ever known. Right? Our improvements are in the order of double digits per year. Whereas if you get, I don't know, 2% improvements in agriculture over a decade, that basically saves humanity from starvation. Yeah, just to give orders of magnitude. So that is true. Unfortunately, the hunger for actual processing time increases much faster than proportionally. To give you an example, to actually process a graph problem, at the origin of graph processing, so just, I don't know, the classic problem of Königsberg bridges, that took about 100 years to solve efficiently. And the big bottleneck was our human brain to actually figure out good algorithms to do this. So mathematicians and computer scientists trying to solve this problem. Right now, with any normal problem, it will take 100 years of computation on your laptop. So although the speed of the current laptop is the speed of a supercomputer's 2 decades back, yeah, it will take 100 years on it to actually solve it. So you probably need a much larger machine. And at that point, we might not have enough electricity for all the problems to be run on all the large machines. So unfortunately, the demand is increasing much faster than the capability. That's Paul Jevons paradox, or at least economists ascribe this. Okay. And now the question, wouldn't co-design, which is the approach in which the application is designed together with the hardware, either first the application matches closely to the hardware, and then if in reality there are still discrepancies, the hardware also evolves, or vice versa. The hardware gets designed for a particular application, and then if in reality there are still discrepancies, then the application evolves. Yeah, so I think co-design is one of the approaches, is one of the major techniques. We also want to do co-design in Graph Massivizer. The problem is co-design can rely on extensive empiricism. So simply you do some design thinking, okay, this should match, and then you measure it, and then you do it again and again and again and again. If you do this, I think that's a dead end, because the space is really huge. So this bad triangle is really problematic because it means the application, which we take as, okay, just look at it and you learn its properties, actually means the algorithm and the data set, with the data set exactly what data is in it, and the algorithm exactly what implementation you get, even of the simplest breadth first search, let's say. This combination is very difficult to capture and may actually be a myriad of sub-problems to actually optimize for. So code design is very difficult to do for this space. These are highly irregular applications in every which dimension. This bad triangle is a killer. So yes, I think this is one of the techniques. I wouldn't put all my eggs into this basket because it may fail spectacularly due to simply the irregularity or complexity of the problem. But if you are the one, fixing this, if you have the brain, there's a Turing Award. So I'm sure there could be in the future a Graves Award. So it's a really big problem. If you can solve it, you'll make a big name across the entire field of computing.
Okay, thanks.
Welcome.
Hey, Alexandru, I had a question. So this is very impressive. I mean, I can understand the scale of this problem is enormous. So, and the level of detail which you're going at, the resource management and all the benchmarking, I mean, it's a non-trivial task. I was just wondering, for one, what is the time frame it takes for one of your largest, graph simulations? What's the time frame?
Thanks, Dirisha. It really varies. So the smallest data sets, they run in seconds or even sub-second time. The medium scale data sets, they run on a good cluster in the order of minutes. The largest, we cannot run them on the biggest supercomputer in the world.
I can imagine.
Cannot, not in our lifetime.
That was my guess.
So you really cover with this every time granularity you can imagine, unfortunately.
One of the things I haven't seen in your analysis, and it can be quite challenging, but because you have a lot of data points across the abstractions, do you think you could have any kind of measures on how much power these systems are taking at any abstraction? That might be a very powerful data point in general. So
it's a very nice suggestion. So we're starting to collect energy consumption data at the various granularities that occur in these systems. So first on the hardware, starting with the performance counters, I don't know, CPUs, networks, etc. And then going upwards into, I don't know, clusters or entire data centers. Until now, we didn't have the equipment. You really need either very good software tools that can measure things at the level of, for instance, of the CPU. The Barcelona Supercomputing Center released something this year. So we're collaborating with them to now target it at graph processing. It's called EAR, EAR. That's the tool from the Barcelona Supercomputing Center. Before we had a more brittle tool called Liquid, and that was also decent, but not across everything, only the CPU.
Right.
And the data centers are starting to install actual power meters. So simply, voltmeters and other kinds of meters at all levels. And we want to leverage this. It's a spot on question. It's in a sense that it's the $1 billion question, because up to now, all our regular energy measurements are so coarse grained that we can't ascribe for different levels of abstraction what happens. Perfect question. But I don't have a better answer. So we're trying to do this.
Good. I think just that thought and just awareness that this has to be integrated in the design flow or in the modeling flow is very important, because the largest savings in some degree can be coming from the choice of the right algorithm and the right software stack, which has often been ignored because we are so performance driven. So
for sure.
Yeah.
So building on that comment, do you think we will get to the point where we will have probably a language? A language might be needed to express all these different characteristics, so that at the end you have an optimization problem, but you need a way of expressing it.
For sure.
So that you choose the right hardware, the right everything.
For sure. So in this reference architecture, the front-end services, what they do is they start with a core programming model. It could be Spark, for example. Spark is a generic programming model for any kind of big data processing. It's a programming model that focuses on a lot of data, also needs to include a lot of definition capabilities for the actual data, the structure, the model, etc. But most people cannot program at this level of abstraction, the programming model. So then high level, especially domain specific languages help there. And even there, many people prefer not to develop at that level. So they prefer to develop in a sense with either zero code. So then you have like a desktop or portal, you drag and drop things, things of this nature, or through a netbook that allows you to somehow load a sort of higher level language based library or something like this. I don't know. So to get back and answer your question, the programming model, not language, any programming model can be, of course, bound to, I don't know if an infinity, but at least a large number of programming languages. The question of the programming model is not solved. And what I think will happen is exactly what I said happened with these platforms. There are just tens of them, and many of them have their own unique domain-specific language, at least, if not even a programming model that is unique. What will happen is, in my prediction, there will be tens to hundreds of these programming models or high-level languages. And then out of these tens to hundreds, all these flowers, some will really bloom. So they will get enough traction and acceptance that they will be used, let's say, for longer periods of time. If that happens, if they serve first, the history of computing shows that this is what's probably going to happen. If that happens, none of them will probably win. So there's not going to be one that is the best. And in that sense, you're still back to the notion that you have a multitude of these things that coexist, and you have, for each of them, you have to provide, well, the same capabilities. You know, can we run this thing? Can we be efficient, et cetera, et cetera, et cetera. It's a very good point that the programming model really has a tight interplay with the backend services, with the system. We just don't know what it is at this point. That's a completely open field. Nobody knows what are the capabilities and limitations of the programming model related to what the system, the layers 1 through 4 can actually do for you. Nobody knows. No theory, very few experiments. Yeah. So another of the open problems.
As a follow-on to Gabriella's point, it's
a nice sequence.
The choice of program. We have a lot of team spirit here. You can see that. So the programming languages themselves are pretty power hungry, right? There's a lot of studies that are coming up. It's like, we have to go back to C instead of a lot of these higher level languages, including Python, which is very expensive in terms of energy. So maybe that's also the choice to be thought about in what is that higher level language we are going to pick up.
Yeah, it's tricky because starting with this level, there are hundreds of other services and things that have to work at the other levels. And we simply don't know if the efficiency is gained with one approach at the programming level can actually be considered as real savings overall. And we don't know. Yeah. So even if the language works, then for this particular area, the applications are so irregular that unless you clearly explore the pad triangle, then you have only a data point out of the entire space. And I just don't know. I don't know.
It is indeed a large scale problem, and I'm glad you're working on it, Alexandru.
Thank you. The community is huge. So for this CACM publication, for instance, we put together 50, good scientists at all levels of their careers, different genders, etc. But from 3 different communities. So computer systems, that's what I represent in this talk. I'm not, of course, the only one working on this. There are hundreds even at supercomputing. Data management, and they really know a lot about data and how to query, etc. And the third is performance engineering. And this is not the end of whom you should get into the discussion to actually solve this. It's a really big problem. Thanks for noticing this. Yeah.
Thank you.
Okay. Do we have more questions? Alan said that it was an awesome presentation.
Thank you. I appreciate this. It's online. Yeah. So just okay. Let me go to slide 1. If I can. Yes. Yeah. Just in case, just download the slides and ask questions later, for example, in the follow-up.
Excellent. Thank you so much. Thank you, Alexandru. And I hope I'll see you more often than every 10 years or so.
Let's do this.
Last time, you were at our 10-year graduation celebration. So hopefully we'll.
I have 0 recollections. I must admit, 10 years is a long time.
Yes, 10. Yeah, I think so. Well, thank you again, and we'll stay in touch, and we'll follow your work very closely, and we'll stay in touch.
I appreciate
Thank
this.
you.
Thank you. Have a good day, everyone. Bye. Thanks for inviting.
Bye.